So the other way of doing this is we could have written it as the condensed one. So we can do this. With the line on the outside, and so it's assumed obviously the connections would be along those carbons. Now I chose to draw them both up, but you could have actually drawn one up, one down, right? So let's say for the original monomer, or you could draw them both down. To be honest, it doesn't matter which direction you kind of push it to. It's just so that you can have the double bond on the same line as the other double bonds that are going to be connecting. Now I'll show you a very common mistake that I see is students will draw the monomer straight. So let's say we did this, so same molecule. I'm only going to draw two here because you'll get the idea of what I mean. Okay, so what they'll do is they'll do this, and then they'll basically just add them up. So there's 4, so we'll have 8. 1, 2, 3, 4, 6, 7, 8. And then they'll do this. Okay, but that's not true. The connections are happening here and here, not at this end and this end. By drawing it straight like this, you are saying that this is basically ethene, right? So just be mindful. I would recommend you draw it this way because it's easier to, I guess, visualize where the connections are going to be happening. Okay, so before we get into this next one, I'm going to give you one to try. Do 3 repeating units of, let's do 1 fluoro, I guess we want to make of the monomer 1 fluoro, 2 methyl, 1 fluoro, 2 methyl, 3 hexene. So actually change this to just being 2 because that's going to be a long one. Okay, give this a try. Okay, so we're going to draw this out first. 1, 2, 3, double bond, 4, 5, 6. Carbon 1, there's a fluorine. Carbon 2, there's a methyl. Okay, and everything else is actually normal. Okay, so do that, plus you do the same thing again. All right, so you can have a whole bunch of stuff on there, different groups, but the process is the same. So I'm going to do the condensed one here. So you're going to have 1, 2, 3. This is now a single bond. And everything stays put. Okay, so that's an addition polymer. Now, the polymer process itself, sorry, I'm just going to move this up a bit. The polymer process itself happens in really 3 different stages. Obviously, it's going to be more complex than just what I'm showing you here or what we're even going to be discussing. But really, at this point in time, this is enough for us to have an understanding of what's happening. So originally, first you need to begin the process of breaking the double bonds. Okay, so typically there has to be some sort of energy that is applied, or you have to have, sometimes you will have a free radical electron that is added to kind of get the chain going to break, like to get all of those monomers to start breaking their bonds. Because obviously if we don't do anything, they're relatively stable together. So it's not like we're adding hydrogen or adding waters. we basically just have our ethene, ethene, mostly it is, but we have our alkenes just kind of hanging out together. So you have to get that process going. So you need to have some sort of initiation. So then we have propagation, which actually is naturally done. Once you have the bonds that are breaking, the monomers will begin to link up because the carbons on either end of the double bonds are requiring additional bonds. So they will essentially link up with one another. So that's just propagation. So the reaction is essentially happening. Now, at the end of the reaction, you have to imagine at the end you're going to have, let's say here's my chain. 2, 4, make it even. So at the end of the reaction, you're going to have 2 carbons that are going to be lacking bonds because let's say you run out of monomers. What ends up happening is typically the carbon still needs a bond. So what it will do is that it will actually link to another growing chain. So let's say we had 2 of those, or make this one smaller. So this one needs a bond and this one needs a bond. Well, this chain can link up with this chain. Perhaps this chain can link up with another chain. You'll always have the chains essentially being linked up to one another. So you'll work out, it will end up working out that all the carbons will have their bonds. So you end up with this huge kind of grouping of monomer chains, right? Which is essentially the whole point of making a polymer. But that's kind of the original process that's done. Obviously, I'm kind of generalizing it here. There's many more. It's not like, oh, okay, we're just going to initiate this and then it's going to happen. It also involves, many different things. You may have to have special equipment to do this. So this is just to get you the idea going of like what is happening here. So properties, I mentioned, the intermolecular forces truly depend on what substituents or what things are bonded to your addition polymer, right? You can have, let's say, an OH group that's repeating. So maybe there's an OH here, and then it would be repeating, right? You will have a whole bunch of different hydrogen bonds. So they can range anywhere from simply nonpolar, like LDF only. You can have van der Waals, meaning you can have dipole-dipole, or you can have hydrogen bonding and have it be a very strong plastic. So it kind of, I know this is just a general statement here, but it really depends. You can't generalize polymers. You have to look at the polymer itself to make that decision. Now, in terms of intramolecular forces, all polymers are created with covalent bonds. Remember, we have, especially addition polymers, the base of it is all carbon-carbon single bonds, which we know are sigma bonds. So in terms of the intramolecular forces, it's actually quite stable. So imagine, I'm just going to kind of show you a picture. Okay, let's say this is a polymer chain, another polymer chain, another polymer chain. The bonds between atoms are pretty stable and strong, right? So they're covalent bonds. But it's the forces between the different polymer chains that will determine its flexibility or its strength. So if you have only LDF happening here, that means you have an incredibly moldable plastic that's very easy to use because you have not really strong connection between the different molecules. So you're able to, I guess, move them around easier. However, if you have hydrogen bonding, let's say, it's going to be a much firmer, denser piece of material. So it varies. It's kind of hard to talk about because you have to look at it on a molecule per molecule basis. Okay, so here's an example of something that has other substituents or other branches, right? So Teflon. So Teflon, I'm sure you have heard of at some point in your life, maybe not. But Teflon is a coating that's essentially used on different types of cooking ware and other various materials. But essentially, it's known as being non-stick, like a non-stick cookware coating. Now, what it's actually composed of is tetrafluoroethene. So here's the monomer to make our polymer. So it's ethene, which with basically instead of hydrogens here, we have all fluorine. So it's very non-polar, right? So when you have this being bonded together, right? So we have the carbons are all now all single bonds. And take a look at the name. We're just going to simply put poly in front. Polytetrafluoroethene. So this is very nonpolar, which makes sense because if we want food to not stick, you should be using something that it doesn't like to stick to, such as something that's nonpolar. Now, the reason why you would use this type of monomer and not any other nonpolar monomer is that they find that this is actually a little bit more unreactive and stable. So you won't have it, coming off very easily. Now, I will say that if you do have a non-stick cookware that has Teflon and there's nicks or let's say by accident, you used a fork and the fork scratched it, when it does get agitated, it can begin to flake off. So that's when it can become dangerous. This is not good to be ingesting. Great as a non-stick cookware material, but as soon as you have some sort of damage to your lining of the Teflon, they do say that it's best to dispose of it and get a new pan. Okay, not that I don't have any stock in pots and pans here, but just for your own safety. Okay, so here's another polymer that's made with different branches on it or different groupings. So this is plexiglass, or the monomer that's used to prepare plexiglass. So really the bond breaking process is happening right here. And the branch that's here is actually, if you take a look at this, this is an ester, or at least a branch of an ester, a portion of an ester. So when you're looking at this, you have to understand that this is, of course, polar, okay? So polar items typically attract polar items, of course, but the closer in structure that two molecules are, the more soluble they are with one another. So for example, there's no hydrogen bonding going on here. So that's why, plexiglass and water don't really go together very easily, right? But if you were to apply a molecule that has a very similar functional group to it, it actually will have some solubility. So if you have plexiglass and you have acetone, not that I'd recommend you try this out at home, especially if you have something made out of plexiglass, but acetone has been known, or propanone, right, it's a ketone here, has been known to be able to be soluble with plexiglass. And it's just because it has a very similar grouping to it. So just kind of something to keep in mind when we're dealing with polymers, right, that's a thing. Okay, cross-linking. So this idea is, it sounds more complex, I think, than it is. So what happens is, remember I mentioned that, let's go back to this picture I drew over here with my squiggles. So remember I mentioned how the bonds that are in the actual polymer are relatively stable, right? All are sigma bonds. But the intermolecular forces can sometimes be weaker. Like they can be strong, but they can be weak. Cross-linking is essentially a way of, instead of relying on intermolecular forces, what we can do is actually bond the different polymer chains to each other. So instead of having these individual chains, we actually have bonds that are linking them to create, it's almost like now we're creating one massive molecule. So it becomes essentially like a sheet of these polymer chains that are now interconnected and bonded to one another.